Welcome to the 8th lecture on module theory. Today we will discuss exact sequences of modules. We start with the definition of exact sequence. So, a pair of R-linear maps, let us say phi and psi, where both are R-module homomorphisms. So, phi is R-module homomorphism from L to M and psi is R-module homomorphism from M to N. Then this pair of R-linear maps or this sequence, it is called exact sequence, or more precisely it is called exact at this point if image of this map it is same as the kernel of the next map. So, note that image of phi and kernel of psi both are submodules of M. So, if they are equal, then this kind of sequence we call it exact sequence. So, this sequence it can be finite or infinite. So, here you consider a sequence that is indexed by integers. So, here indices are increasing. Okay. So, this kind of sequence we call it a complex if composition of any two successive maps it is 0. So, first you take this map and then you compose that with this phi n, you will get 0. That means you have this equality, and this thing is equivalent to say that image of this map it is contained in the kernel of the next map. So, if this is there for all n, then this kind of sequence we call it a complex, and a complex it is called exact sequence if we have equality here. So, in other words, image of each map if it is same as the kernel of the next map, then this kind of sequence we call it exact sequence. And an exact sequence of the form this it is called a short exact sequence. So, it is starting with 0 and ending with 0 and its length is 5. So, this kind of exact sequence we call it short exact sequence, and it turns out that any exact sequence you can break it into a collection of short exact sequences. Okay. So, therefore, it is enough to study these short exact sequences. Here you consider this sequence. So, this sequence is exact if and only if, so we should have some condition on this map phi. So, this is exact, that means image of this map that should be same as the kernel of the next map, but what is image of this map? It is just 0. So, if it is exact, that means kernel of this map that should be 0. So, I should write then this kind of sequence is exact if and only if phi is 1 1 or injective. Next you consider this sequence. So, this sequence is exact, that means image of this map that should be same as the kernel of the next map, but what is the kernel of the next map? So, here you can see that everything is going to 0. So, kernel of this map it is just this whole thing n. So, this sequence is exact, that means image of this map that should be this n. It is equivalent to say that psi is onto or surjective. Next you consider this sequence. So, this sequence is exact, that means at each point it is exact. So, it is equivalent to say, so it is exact at this point, it is equivalent to say that phi is 1 1 that we have already observed. It is exact at this point, it is equivalent to say that psi is onto, and it is exact at this point by definition, then image of this phi that should be same as kernel of the next map psi. Here are some examples of short exact sequences. So, you consider a submodule of M, let us say n, then for that submodule we can have a natural short exact sequence like this. So, n is a submodule of M, that means you can have that inclusion map from n to M, and that map is injective. So, if you consider this sequence, then it is exact at this point. And then if you go modulo n, then you can have this cosine module, and from M to M mod n you can have a natural projection map, namely x is going to x bar, or that is modulo x modulo n. So, then this map is surjective. So, that means it is exact at this point also. Now, what about this point? So, image of this map, you can see this is inclusion map. So, image of this map, it is just n, and what is the kernel of this map? So, kernel of this map again it is n. So, you have exactness here. Okay. So, this sequence it is exact, and even one can observe that every short exact sequence up to isomorphism it looks like this. So, here you consider an arbitrary short exact sequence, that means this map is injective. So, you can think that L it is just isomorphic to phi of L, its image, and that is a submodule of M. So, you can think L as a submodule of M via this map, and this map that should be surjective. So, therefore, by first isomorphism theorem, M mod kernel psi that is isomorphic to n. So, up to isomorphism it is just cosine module of M. Okay. So, this sequence it is exact if and only if up to isomorphism it looks like this. Okay. So, all short exact sequences up to isomorphism they look like this. Okay. So, the second example, so you consider two R modules M and N, then you can consider their direct sum. Then from M to M direct sum N, you can have a natural map, that is injective map, namely x is going to x comma 0. So, M you can think as a submodule of this direct sum, and from this direct sum to N you can have a natural projection map, namely the projection map on the second component. So, x comma y it is going to y. So, you can verify that this sequence is exact then, because image of this map it is just M, okay, and that is same as the kernel of this map. Okay. And this kind of short exact sequence we call it split short exact sequence, where this middle one it is just isomorphic to the direct sum of these two modules. Okay. So, a short exact sequence it is called split short exact sequence if up to isomorphism it looks like this. We will define what is split short exact sequence later in a more precise manner. Third example, you just consider an R module homomorphism, let us say phi from M to N, then by that R module homomorphism you can construct a short exact sequence like this. So, you consider the kernel of phi, then kernel of phi it is a submodule of M. So, you can have this natural inclusion map, that is injective. And if you change this map, so just by changing its codomain, so you just change the codomain to image phi, then this map it is a surjective map, okay, and kernel of this map it is same as the image of this map. So, you have a short exact sequence like this, that is induced by this module homomorphism. Here we define what is split short exact sequence. So, we have already said that a short exact sequence, if it is isomorphic to this kind of short exact sequence, then we call it split short exact sequence. So, here is the precise definition. So, a short exact sequence we call it split short exact sequence if image of this map, that is phi of L, if it is direct summand of M. And what I mean by that? So, that is there exists some module of M such that your M, that is internal direct sum of phi of L along with n prime. Okay. And it is equivalent to say that up to isomorphism your M it is just direct sum of these two things. Okay. So, M that will be isomorphic to direct sum of L and N. So, up to isomorphism they are same, and more precisely your M it is just internal direct sum of phi of L with n prime, where n prime is a submodule of M, and you restrict your this map psi to this submodule, then that will be an isomorphism. Okay. So, namely psi restricted on that submodule n prime, it is an isomorphism. Okay. So, let us prove these two things, that first and this is your second statement. So, these two things are equivalent. So, we can say that 2 implies 1, it is obvious. So, if you have this, then you can clearly see that phi of L, it is just a direct summand of M. Okay. Now, what about reverse direction? So, suppose you have this. So, phi of L is a direct summand of M, that means you have a submodule of M such that M, it is internal direct sum of this phi of L and n prime. So, we need to prove that if you restrict this map on that submodule n prime, then you will have an isomorphism like this. We need to prove that this is isomorphism. So, restriction, so since it is restriction map of an R-linear map, so anyway this is R-linear, just we need to prove that this map is bijective. Okay. So, you consider an element in the kernel. So, let us say this is 0 and that means psi of x. So, this is just restriction map. So, psi of x, it is 0. So, therefore, x is there in the kernel of psi, but you are starting with a short exact sequence. Okay. So, kernel of this map, it is same as image of this map. So, it is same as image of phi. Okay. Therefore, x, it is just phi of y for some y belongs to L. Okay. And then you just so this x, that means it is there in both phi of L and also it is, you are starting with an element of n prime. So, it is there in n prime, but since it is internal direct sum, so intersection of these two submodules, that should be 0. So, this is 0 and therefore, x should be 0. Okay. So, this proves that this map, it is injective. Now, why it is surjective? We need to prove surjectiveness. So, you consider an element here, we need to prove that you will have a pre-image here. Okay. So, since psi is, this map is surjective, there exists an element of M and your M is internal direct sum of this, that means it is just, first of all, it is sum of this, where each element has unique expression. Okay. So, there exists y1 plus y2 in this sum phi of L plus n prime, such that the psi of y1 plus y2, that should be same as n z, because this map, it is surjective map. So, for each element here you will have a pre-image, and since M is internal direct sum of this, so your pre-image will be look like this. Okay. Then you can see that this thing psi of y1 plus y2, so it is same as psi of y2 only, because psi of y1, since y1 is there in image of phi, so this y1, it will be there in the kernel of psi, because you have equality here. So, psi of y1, it is just 0. Therefore, psi of y2, it is same as z, and that means you are having a pre-image here, namely y2, and that will map to z. So, this map is that is surjective also. Exact short exact sequence like this, and this proposition, it is saying that this short exact sequence, it is split if and only if you have a map from n to m in this reverse direction, that is mu, such that this composition psi compose mu, that is identity map on n. Moreover, it is equivalent to say that there is an R-linear map lambda from M to L, it is lambda such that this composition, so lambda compose phi, it is identity map on L. Okay. So, let us prove this proposition. First we will prove 1 implies 2. So, in 1 you are starting with a split short exact sequence, that means by definition phi of L, it is direct summand of M. So, this is direct sum, internal direct sum of n prime, that will be M for some sum module of M. Okay. So, you are starting with a split short exact sequence. Now, you want to construct a map like this. Okay. So, we have already proved that in this situation it is equivalent to say that you just consider its restriction map psi restricted on n prime, then this map it is isomorphism. Okay. So, that means inverse of this map it makes sense. Okay. So, inverse of psi starting from n to n prime, it makes sense, and then you compose that inverse with this inclusion map, because n prime it is sum module of M. So, you can have a map from n to M, and by construction you can prove, it is easy to verify that psi compose mu, it is just identity map on n, because it is mu is just composition map of this psi inverse and this inclusion map. Similarly, one can prove 1 implies 3. Okay. So, 1 it is saying that your module M, it is just internal direct sum of these two. Now, we want to construct a map from M to L. Okay. So, from M to phi of L, you can have a natural projection map, namely the projection map on the first component. So, then from here to here you can have a map, and then from phi of L to L you can consider phi inverse, because from L to its image that map is isomorphism. If you change its codomain to phi of L, then this map is isomorphism. So, phi inverse starting from phi of L to L, it makes sense, and then you can consider their composition. So, again by construction of this lambda, you can verify that lambda compose phi, it is just identity map on L. Okay. So, we should prove the reverse directions. So, namely 2 implies 1 and 3 implies 1. So, here is the proof of 2 implies 1. So, in 2, that means you have this kind of map from n to m such that their composition is identity, and now we should prove that your short exact sequence is split. So, that means we need to prove that this phi of L, it is direct summand of M. So, we need to find a sum module of M such that internal direct sum of phi of L and that sum module it is M. So, most natural choice using this module homomorphism, most natural sum module of M we can consider it is just image of mu, that is mu of n. Okay. So, we claim that M it is internal direct sum of phi of L and mu of n. So, let us prove this. You start with an element of M. First we should prove that M is just usual sum of these two sum modules. So, this x you can write in this manner. So, you just add and subtract this element. Okay. So, then you can see that this element it is there in image of mu. So, it is there in mu of n. What about this element? So, you just apply psi on this. Okay. If you apply psi, then it is just psi of x minus psi of x, because psi compose mu it is just identity map, and so this thing is 0. So, therefore, this element it is there in the kernel of psi, and kernel of psi that is same as image of phi. So, this element it is there in phi of L. Okay. So, therefore, each element of n M, it is just there in the usual sum of these two sum modules. But we should prove that this expression is unique, or equivalently we should prove that this intersection of these two sum modules, that is trivial, that is 0 sum module. So, you consider an element here in this intersection, and we should prove that that element is 0. Okay. So, since x is there in image of phi, that means x should be there in kernel of psi, because this is exact sequence and image of phi, that should be same as kernel of psi. Okay. So, x is there. Since x is there in mu of n, that means x that should be equal to mu of y for some y belongs to n. Therefore, you can write y, it is just psi compose mu of y, because psi compose mu, it is just identity map. Here you have this condition, you are starting with this. Okay. Since this is identity thing, so this of y, it is just y. So, therefore, it is just same as psi of x, because mu of y, it is same as x. Since x is there in kernel of psi, this is 0. So, therefore, y is 0, and hence x, that is mu of y, that should be 0. Therefore, this intersection is trivial. Okay. And therefore, this usual sum, it is just this internal direct sum. Okay. And this proves that this short exact sequence, it is split. Next, we should prove 3 implies 1. So, you start with 3, that means you have this, suppose you have this module homomorphism from M to L lambda such that this composition is identity, and we should prove that this short exact sequence is split. So, again we should find a sum module of M such that M, it is internal direct sum of phi of L and that sum module. So, starting with this module homomorphism, the most natural choice for a sum module of M, that should be kernel of this map. Okay. So, we claim that M, it is internal direct sum of phi of L and kernel of lambda. So, again you start with an element of M, and write your x, you just add and subtract these things. So, then x you can write in this manner. So, this thing you can see that this is an element in image of phi. Okay. Next, we should prove that this is an element in the kernel of lambda. Okay. So, you just apply lambda here. So, it will be lambda of x minus again lambda of x, because lambda compose phi, this is just identity map. So, this thing is 0, that means it is there in the kernel of lambda. You consider an element in this intersection. Okay. We should prove that that element is 0. Okay. So, since x is there in phi of L, so x you can write phi of y for some y belongs to L. Since this composition is identity, so y you can write in this manner lambda compose phi of y. So, this is just lambda of x, because phi of y it is same as x, and since x is there in kernel of lambda, so this lambda of x, that should be 0. So, it proves that y is 0, and hence x, that is same as phi of y, that should be 0. So, this proposition we can see that this short exact sequence, it is split if and only if you have a map from n to m such that this composition is identity, and it is equivalent to have a map from M to L such that this composition is identity, because existence of this kind of maps, it gives that this short exact sequence, that should be split short exact sequence. So, this kind of maps we call splitting homomorphisms.